So the first talk will be given by Nathanaëlle Courant and is co-authored by Xavier, Leroy, and it will be about a lazy concurrent convertibility checker. Please.
So, thank you for the introduction. So, I'm Nathanaëlle Courant. I currently work at OCamlPro, but what I will tell you about today is what I did during my PhD with Xavier Leroy at INRIA about building a lazy concurrent convertibility checker. So, a convertibility checker tries to prove that two things are equal and is critical when writing a proof assistant with dependent types. So, as motivation, let us consider f be an expensive function to compute. And we want to efficiently prove that f of 20 is convertible with f of 20. This problem is easy. Both sides are identical, but we already see that reducing both sides to normal form, the naive version, will be inefficient. Let us consider another problem where we have two different free variables on both sides, and we have x of f of 20 on one side and y on another side. These two terms are not convertible, and again, we need to evaluate f of 20 lazily if we want to prove that efficiently. Suppose now we want to prove that f of 20 is convertible with f of 19 plus 1. So we will use we can prove this efficiently just by proving that 20 is convertible with 19 plus 1. And this is the strategy used by Rock and many other theorem provers to try to prove the convertibility of the arguments first before expanding the function. However, this strategy has drawbacks. So consider for now the k combinator, which returns its first argument, and suppose that we have on one side k of 0 on f of 20, on the other side k of 0 on f of 21. If we try to prove the convertibility of the arguments first, we will perform a very expensive computation, whereas if we unfold k first and compare both sides, we can prove convertibility very efficiently. Sometimes we have two different head constants on both sides, and it's unclear which we need to unfold. So again, Rock uses heuristics to do this. But suppose that here f is the exponential function, and we want to prove that f of 20 is convertible to f of 19 plus f of 19. If we unfold f on the left-hand side, but not plus on the right-hand side, we can prove convertibility very efficiently by noticing that after that we have identical sides. However, if we want to prove that f of 20 is convertible with 0 plus f of 20, with the same head constants on both sides, but different arguments, here we need to unfold plus, and then we can obtain identical sides and prove convertibility. So it's very difficult to know which would be the good option without effectively trying it. So the formal statement of the problem is that we have a lambda calculus with defined constants. So for instance, f or k in the previous examples, which are associated to a term. We have two operations, beta reduction as usual, and delta reduction, which replaces a constant by its definition. The convertibility test is just to we want to ask whether two terms are beta-delta equivalent. In the paper we handle eta as well, but I won't talk about it here. And we make the hypothesis that we have only strongly normalizing terms for decidability, which is the case in proof assistance such as work. But we don't use typing information at all to write our convertibility tests. So the textbook way to test convertibility is to reduce both sides to normal forms and check whether the normal forms are equal. In the presence of strongly normalizing terms, this shows decidability, but it's very inefficient. The standard way, the one used by most theorem provers, is to reduce to weak head normal forms both sides, look if those sides have the same shape, and if they do, we have several other convertibility tests to solve again, which we do recursively. This is efficient if the right unfolding decisions are taken as I showed in the introduction, but it can be costly otherwise. For the large theorem provers, the important ones, they use heuristics to guide unfolding, which are not always successful. So what our proposal is instead to have a concurrent execution of both convertibility tests and evaluation steps, everything computing concurrently, and try to find solutions as early as possible. So for that, we start by expressing laziness as a process calculus. So we have an infinite set of channels, alpha, beta, and so on, and processes which can reduce a given term m to a value and send it on a given channel alpha. They can be any term, and they may use alpha question mark to read a value from alpha and continue once the process on alpha has finished computing it, has finished computing a value and continue with that value. We can execute processes concurrently, and we can generate fresh channel names. The most important rule is the communication rule, where if we have a process waiting on a value on alpha and another process which has finished computing a value on alpha, then the first process receives the value, and we keep the other process in case other processes ask again for a value on alpha. This can be used to represent non-strict evaluation, where a lazy value is simply a channel name. Creating a new lazy value, to create a new lazy value, we create a process which evaluates the term and sends it to a channel, the channel which represents the lazy value, and forcing the value is simply waiting for a value on that channel. So nothing in that enforces real laziness. We only have non-strict evaluation. The lazy part comes from the scheduler, which will not reduce m in alpha bound m until alpha is itself forced. So until some other thread is waiting for a value on alpha. And with these notations, so we can write a convertibility test between two terms, T1 and T2, as a convertibility process, conv, which asks for two weak head normal forms, which it will receive on channels beta and gamma, and two processes, eval, which reduce the values to weak head normal form and send these results. We also have a mapping between three variables of both terms, as usual, to deal with binders. So what do our weak head normal forms look like? The core idea is that we have a channel for lazy evaluation of function bodies and unfolded constants to avoid recomputing them repeatedly if we ask several times for either the function body of a closure or what happens when we unfold a head constant. So for a closure, we have the usual part, so the variable on the closure, an environment, and also this channel beta, which evaluates the body of the function with a new head variable, a new parameter. We have neutral terms for free variables, which is simply a free variable applied to a stack, a list of channels. And for constants, they look like free variables. So we have a given constant with a definition, a stack, and a channel which evaluates the result that happens after we unfold the constants. So we will first consider the concurrent convertibility test in the context of the pure lambda calculus. So if we want to compare two lambda terms, two functions, two closures, we simply need to compare the function bodies and extend the free variable mappings to say that both parameters should be considered the same. If, on the other hand, we have free variables on both sides, we simply compare the stacks and check that both head variables match. And in all other cases, since we don't consider eta in this talk, they are not convertible, so we can immediately conclude that we stop with a result of false. Comparing the stacks is where it gets interesting. So if only one stack is empty or both stacks are empty, it's either false or true. But if both stacks are non-empty, we generate two fresh convertibility tests, one for the head of the stack and one for the rest of the stack. And we combine them. And here we see this is done concurrently because the process on alpha is waiting for two other processes. So the two other processes will compute in parallel. And with short-circuiting semantics for here the AND Boolean operator, as soon as either process concludes with false, we will immediately conclude that both sides are not convertible without waiting for the rest of the computation to have finished. If we have constants, we have other rules as well. So if only one side is a constant, we don't really have a choice. We have to unfold it. But if both sides are different constants, we have a choice. And this is what I told in the introduction, that we don't know which one to unfold. So thus, the idea is to unfold both in parallel. So on one side, we unfold the left constant. On the other side, we unfold the right constant. And we do this concurrently. And we know that both unfoldings will give the same result in terms of convertibility of the argument of both sides. So we have this choice operator where A choice B is B, assuming that A equals B. This is not a normal Boolean operator because it's not interesting if seen as a Boolean operator. But if we look at it in terms of computation, this is an operator which short circuits as soon as either side is computed and stops with this result. And finally, the most interesting case is if both heads are the same constant. In that case, we can unfold either, but we can also compare the stacks and see if they match. If they do, we know that both sides are convertible, but if they don't, we have no information. So we have this new operator biased choice here, where A biased choice B is B, assuming that A implies B. And this will short circuit if A evaluates to true, not false, sorry for the error, or when B is computed. So, with all these rules, we can prove convertibility efficiently, and we expressed what this efficiency means. So, we assume that we have a given set of rules to prove convertibility or non-convertibility of two terms. We give them in the paper, and we prove that the complexity of our algorithm is, on the worst case, exponential in the size of the shortest proof. This looks like a lot, but strategies with heuristics such as inside VOC cannot be bounded by any computable function of the shortest proof, so it's a very clear improvement. In practice, it's even better than that, because this worst case exponential happens only very rarely. And in practice, it's linear or almost linear. We have done a work formalization of the correctness of our algorithm. So we have proved the reduction rules which I have not shown, and the convertibility rules are correct with respect to beta and delta reduction. We have extensions to support constructors and shallow pattern matching, but we do not formalize the scheduling, so we do not have a formalized proof of complexity. All in all, the proof is about 10,000 lines, so it's moderately sized development. And it gives confidence in the correctness of our algorithm. We also do a lot of additional things in the paper, which you can look at. So we handle eta conversion. We avoid redundant unfolding of constants. So if you have two different constants on both sides, A on one side and B on the other side, with the algorithm I presented, we can unfold A, then B, and get some test, or unfold B, then A, and get another test. And with what I just presented there, I not shared, but we can avoid that. And we can even have additional sharing between identical source terms and between values that we encounter several times on both sides. We also present an explicit scheduling algorithm to show that it can be realized, which keeps a list of active processes. So active processes are those that are useful and needed for the evaluation to complete. And once a process becomes inactive, then we remove it from that list, or we add it to this list, depending on whether we need to execute it or not. So, in conclusion, we have a convertibility test for lambda terms with definitions and constructors in the Coq formalization, with worst time complexity bounds, depending only on the size of the shortest proof of convertibility or non-convertibility. It is formalized and verified in VOC, and in the future we plan to extend it to other features of VOC, such as cofix points, universes, S-prop, and so on. We think we can get a bit better complexity bounds by improving the scheduling of processes. And we also want to produce proof traces and replay them to be even more efficient when checking the proofs. Thank you for your attention.
Thanks a lot for the talk. And are there any questions?
Do you believe the exponential optimality gap is optimal, or could there be an even tighter algorithm?
Not without changing the algorithm. We have some worst case examples where we are indeed exponential. So we would need to change the algorithm for that. But it seems like it doesn't happen so much in practice on the test we did.
Hi, thanks for the talk. This might be, it might be that I've just not internalized everything that's going on here, but does this algorithm split into sort of a purely non-deterministic but not concurrent algorithm, and then sort of a concurrent way of running a non-deterministic algorithm? Like, can you see this algorithm purely as taking non-deterministic choices while evaluating things?
Yes, so the idea to replay post traces is simply that when we have these short-circuiting operators, we could simply annotate them with the side that short-circuited, the side that computed. And if we want to replay a post trace, we simply just ignore the side that did not short-circuit. And so this is the only non-deterministic part.
You retrieve the usual reduction, the usual convertibility test by the choice of an appropriate scheduler, or is it completely unrelated?
So yes, if you almost there's a bit of mutable state inside of Vox convertibility test. So this is not replicated, but for instance, in this choice, in these cases of having two head constants, the same head constants, if we only compute the left side here, and only if it fails compute the right side, we will get exactly the same thing as ROC does.
So,
yes.
That's really cool work. So, I was wondering, a lot of the actual conversion-like things that happen in kernels is more akin to unification. And do you think that, like, basically the same ideas would also be applicable to a unification solver, or do you think they would need really something different there?
I've started to think about it, and I think it could be applicable, but it's not obvious because sometimes there are, depending on which branches you take, there may be several unification possibilities. So for instance, here you could prove convertibility of arguments with a given unification, but if you unfolded, you could see that this was not needed, and you didn't need to do that unification. So that I think there would be some additional ideas needed to conclude, to do something for that.
Thanks.
Okay, I think this will be the last question.
Great talk. So how does, can you prove that this algorithm is asymptotically more efficient than a breadth-first search of the derivation tree?
It's essentially a breadth-first search of the derivation tree, but so I've not talked about it much in this talk, but we need to share the computations on the different branches, and this is possible because of our process formalization. But without sharing, it would be a lot less efficient.
Okay, I think it's time to move on, and let's thank the speaker again.